Hi everyone. So in this video, we're going to be continuing to talk about limits, but we're now going to be focusing on finding limits by looking at a graph. And specifically, we'll see that using graphs is especially useful when we're talking about piecewise functions. So we'll get into really focusing on piecewise functions for most of this video. Before we do that, I just want to refresh your memory on what a limit means and kind of summarize, what we already talked about with limits and then where the topic of limits is going to be going over the rest of this week. So last time we talked about that the limit as x approaches a of a function, it's basically just asking you, what is the trend? Where is the graph? Where are the y values of the graph or the function heading when x is getting closer and closer to a particular x value? So when you're evaluating a limit, you're not usually plugging in that x value, because usually when you're taking a limit, it's because the function is not defined at that x value. We'll see actually later that there are circumstances where you can evaluate a limit just by plugging a number in, but for now, those aren't really the circumstances we're looking at. So instead, what we're doing is we're looking at not what's happening at that specific x value, but what's happening when you're close to that x value. And so the way that we kind of describe that is we say that x is approaching a. So we're looking at x values that are close to a. And then we look at where are the y values, where are the outputs of the function going, and the value that the outputs are approaching, we call that L. So if we write down the limit as x approaches some number of f of x is equal to some other number, that means that as x approaches a, and so one thing that we talked about last time is that it's not just x approaches a from one side, it has to be from both sides. And so when we say from both sides, we basically mean if you plug in a number that is, just a little bit less than a or just a little bit more than a, that's what we mean by from both sides. So f of x approaches L. And again, it's kind of like a way of getting around plugging in a number. Instead of plugging in a particular x value, you're kind of poking around it and seeing what's happening when you're close to that number. So there's going to be, we'll see basically like three main ways to evaluate limits in this class, and I want to write those down. So the main ways to evaluate the limit as x approaches a of a function. So the first way is what we talked about in yesterday's video, right? We talked about plugging numbers in. So the way I'm going to summarize that is we plugged in numbers closer and closer. So it's really important that when you're doing these limits by plugging in numbers, you're not just picking like one number that's close to the number. You want to you have to be able to observe a trend. So, if you're trying to plug in a number close to 3, that's where you plug in like 2.9, 2.99, 2.999. So you want to make sure you're getting successively closer. So that's why I say not just a number close, but I say numbers closer and closer to A. And see what happens to f of x. So the reason that I show this as the first way of evaluating limits is that I think it's a good way to kind of build intuition for what limits really are. But we'll see that this is actually not really the method we're going to use. Basically, yesterday was really the only video where we're going to focus on plugging in numbers to find limits. We'll see that today, focusing on graphs is going to be one method, and then we'll have another method we'll talk about later this week. So I want to give you an example of why this method of plugging in numbers maybe isn't so good. So just going to kind of make a note here that sometimes this method is misleading or it just doesn't work. Maybe I'll put my little warning symbol. So an example of where this method would kind of fall apart is, let's say that you were trying to evaluate the limit as x approaches 0 of sine of pi over x. So why would we be doing a limit in this circumstance? Well, because you can't plug in 0, right? Pi is a number. So if you do pi over 0, that's undefined. And so it just doesn't even make sense to take sine of something over 0. So that's the reason that we would have to do a limit. So if you were doing this problem, the way that we described in yesterday's video, you would probably do something like this. You would say, okay, let's pick some x values that are just below 0. So that would be like negative 0.1, negative 0.01, and negative 0.001. And then we know that at 0, it's undefined. And then if you're plugging in numbers above, you would probably plug in something like 0.001, 0.01, and 0.1. So let's see what happens when we plug a few of these in. We're not going to do all of them because I think just doing a couple is enough to see what happens. So let's say that we wanted to plug in this first one, negative 0.1. So if we do sine of negative, let me write it like this, sine of pi over negative 0.1, that's going to be the same thing as sine of pi over negative 1/10, right? 0.1 is the same as 1/10, so we could rewrite this as negative 1/10. And then what's another way of writing pi divided by negative 1/10? Well, that's the same thing as negative 10 times pi, right? Because dividing by a fraction is the same as multiplying by its reciprocal. And so what is sine of negative 10 pi? Well, any multiple of pi, sine is going to be 0, right? Because if you think about on the unit circle, so trigonometry is not going to go away this quarter. We're still going to be using it, and I'm going to expect that you're very comfortable with the basics of trigonometry in this class. So sine of 0 or pi or 2 pi or 3 pi, any number that's a multiple of pi is going to give you a point on the unit circle that either has coordinates of 1, 0 or negative 1, 0, right? So any sine of any multiple of pi is always going to be equal to 0. So we get 0 here. Now, if we try the same thing now with the next value, so sine of pi over negative 0.01, well, that's the same thing as sine of pi over negative 1 over 100th, or 1 over 100, right? Because negative 0.01 is 1/100th. And so that's the same thing as sine of negative 100 pi. And same deal as what we saw over here, that's still a multiple of pi, so you still get 0. And basically the same thing is going to happen for all of these, right? Like anytime you're plugging in 0.1, 0.01, 0.001, if you simplify it, you're going to end up with a multiple of pi and you're going to get 0. So from this, you would probably conclude, okay, that means that the limit as x approaches 0 of sine of pi over x equals 0, right? Looks like it based on our table, because everything else is pointing towards 0. However, that's actually not correct, and I want to show you the graph so that you can really see that it is not correct. So this is the graph of sine of pi over x. And notice that the graph, I'm going to zoom in, and it's kind of crazy. The graph is going to just it goes up and down so rapidly that as you zoom in, it's almost like you're walking down a hallway or something. But see how it kind of looks like one solid block here? It's not really one solid block. It's just that the graph is going up and down so quickly that you have to really zoom in to see what's going on. And so the further you zoom in, the more you just see this quick repetition back and forth. So this is actually a situation where the limit does not exist, and it doesn't exist for different reasons from what we've seen before. It's not really the left and right hand side thing going on. It's just that this function is so crazy that there just is no limit as we approach 0. So basically what happened is that we just happened to pick some very lucky numbers, because there are places, we can even see it here. So like if you were to plug in 0.2, it looks like you get 0. Or here we have point, I don't know, all of these points here, right? The graph does cross through 0, but we just happen to get lucky and pick points that did that. But there are plenty of other points where it's just going haywire and going up and down. So long story short, that's just to kind of show you that you can't always trust plugging in numbers. So really, the limit does not exist in this case. And I wouldn't expect you to be able to figure that out unless you looked at the graph. And generally, we're not going to be doing examples that are like as kind of strange as this function. So the point of showing you this problem is really just to illustrate that like there are cases where plugging in numbers leads you astray. So that's one of the reasons that we're going to be kind of leaving that method behind in this video. So the other method we're going to be, and what we're going to be focusing on in this video, and what we kind of just did, is looking at the graph. So the second method is to graph f of x and basically see what happens to the y values on the graph when x is close to a. So basically just kind of looking at, what is the trend as you get closer and closer to that limit value, what's happening to your y values. So for example, on the graph we just looked at, the closer you get to 0, the more crazy the graph gets. And so that's why the limit did not exist. But we'll see some more straightforward examples of this today. And then the method, and maybe I'll just say, I'm trying to not mention today, tomorrow, and etc. because of the way I'm setting these videos up. So I'll just say this video. And then in the next video, the focus is going to be actually on using algebraic methods to simplify. And that's going to end up being like our main method of evaluating limits. So use algebraic simplification. And we're not talking about that today. We'll get into it in the next video. And I think actually that'll probably be like the next 2 videos because it's really important. Okay, so a whole bunch of intro, but now let's actually get into the meat of this video, which is using graphs. So as I mentioned, really one of the main reasons to use a graph to evaluate a limit is when you're dealing with piecewise functions. So I want to look at a piecewise function and evaluate limits using it. So let's say that we had the function f of x is equal to, so what is a piecewise function? It's a function where you don't just have one formula, you have multiple formulas, usually, 2 or 3, but it could be more. And you have different rules that tell you when to use each formula. So this one we're going to do says that you use the formula 2x plus 1 if x is less than or equal to 0. And you use negative x squared if x is greater than 0. And so the problems that we're going to answer in this is we're going to figure out what is the limit as x approaches 0 from the left of f of x, the limit as x approaches 0 from the right of f of x, and then depending on whether those two agree or not, that's what will enable us to either find the overall limit of f of x or just say it does not exist. But before we try to answer the limits, let's actually graph the function because that will make it a lot easier to figure out what's going on. So how do you graph a piecewise function? Basically, you just think of it as kind of 2 different pieces. So we can start with this top function and just graph it. So 2x plus 1. So that's a line with a slope of 2 and a y-intercept of 1, right? So it's going to look something like this. And when I am graphing piecewise functions, I like to just kind of graph the whole thing and then we'll erase out whatever's the part we don't need. So this formula is specifically, it says that you're supposed to use this line if x is less than or equal to 0. And so that means that we don't want this top part of the graph. We only want this, right? We want everything kind of from below 0 all the way up until 0. And notice that I put in this solid dot. That's to represent the fact that, we said less than or equal to 0. So when you're graphing a piecewise function, you use the open circles to represent if you're not supposed to use the graph at that point, and you put a closed circle if you are supposed to use that part of the graph at that number. So because when x equals 0, we're using this part of the graph, that's why I put the closed circle. Okay, so next part is negative x squared. So again, I'm going to start by just drawing it without thinking about restrictions. So negative x squared is a upside down parabola. So it would look like this. But again, we don't need this whole thing because we're only supposed to use this part if x is greater than 0. And so that means we'll get rid of this negative half and we're just dealing with this part. And then because this tells us only to use that part of the graph if x is strictly greater than 0, that's why we put an open circle here. Okay, so now let's look at this graph and use that to guide us to figure out what is the left-hand limit, what is the right-hand limit, and what is the overall limit if it exists. So when we're finding the left-hand limit, so this first thing, the limit as x approaches 0 from the left, we're basically trying to go towards an x value of 0, but we're literally like, picture you're like walking on the graph towards it and you're walking from the left. So we're coming in this way and we're trying to see where is the graph headed, where is the function headed. So if you're coming in from the left, the graph is heading towards a height of 1. Right? Like the closer and closer you get to an x value of 0, if you're on the left, then your graph is creeping closer and closer to a y value of 1. And so therefore, the answer is 1. On the other hand, if you're coming in from the right-hand side, so you're plugging in values that are just to the right of 0, well then the graph is actually heading towards a height of 0, right? So even though we have a hole in the graph at x is equal to 0, remember that when you're doing limits, this is like the most important thing to know about limits. Limits don't care about what's happening at a particular x value. They only care about what's happening close to that x value. And so even though the function is not defined at x is equal to 0 on this part of the graph, we can still kind of assess what's going on as we get close to there. And so as you get close to 0, if you're plugging in numbers that are just above 0, the function is heading towards a height of 0. And so therefore we say the limit is equal to 0. And then to evaluate the overall limit, well, the left and the right-hand limits do not agree, right? They don't match up. And so we would say that overall, the limit does not exist, because you really would need to specify whether you're going from the left or the right to be able to give an answer. So there's one other thing I want to mention from this picture, which is actually evaluating. So this is a case where we actually can evaluate f of 0. So that's kind of a separate thing. It doesn't really, it's separate from limits, but it's something that I want you to still understand how to do from a piecewise function. So if we wanted to evaluate f of 0, that would mean that we're saying, what is the y value on this function associated with x is equal to 0? So there's two ways to do it. One is we could look at the piecewise function, the formula, and just see where are we supposed to plug this in. And we're supposed to use the top function if x is less than or equal to 0, right? So when x equals 0, we want to use the top function. And if you use the top function, you find that f of 0 is 1. You could also find that looking at this graph, and it's because if you're going to an x value of 0 and you're seeing like where is the point on this graph with an x value of 0, you see that we have this point 1. And so that is f of 0. Okay, let's do another example. So this is going to be a slightly different kind of piecewise function. So this one is going to be f of x is equal to, or maybe let's call it g of x. G of x is equal to sine of x if x is not equal to 0, and it's equal to 1 if x is equal to 0. So how do we go about graphing this one? Well, basically, this is going to look almost just like the graph of sine of x. The only problem is that it says if x is not equal to 0. And so what that tells us is that there's going to be a hole at x is equal to 0. So the graph of sine of x has, we typically think of it kind of starting at 0, 0 and going up, and then it would later go down. But, that part is not really included on our graph. And then if you think about what it's doing on the other side of the y-axis, it's kind of doing the opposite shape. So it's like this. And then I guess I didn't do a good job of this, so let me fix it. So there should be a hole at 0, right? Because it's specifically telling you not to use this function when x equals 0. And then what are we supposed to do when x equals 0? Well, we're supposed to use the second function. And so that means that we should have a point 0, 1. So that is our graph. And we're going to do the same thing basically that we did in the last one, which is answer, what is the limit from the left, the limit from the right, etc., all of that. So let's find the limit as x approaches 0 from the left of g of x, the limit as x approaches 0 from the right of g of x, and then we'll see if we can find the overall limit. Okay, so from the left, we're kind of just coming in towards 0, plugging in numbers or looking at the graph just to the left of 0. And we're just looking for where is the graph heading. And so the graph is heading towards a height of 0. We know that there's a hole there, but that hole doesn't matter because we're just talking about the trend. And the graph it looks like it should be going to 0, right? Even though there's a hole there, it seems like there should be a point at 0, 0. And then similarly, if we're taking the limit from the right, in this case, the graph is going down, 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 also getting closer and closer to 0. And so the limit from the right is also equal to 0. And then what about the overall limit? Well, because both the left and right agree, we can say that the limit as x approaches 0 of g of x is equal to 0. However, if we go to evaluate g of 0, that's where we have to actually look at our function and then look at our graph and see that, well, if you plug in 0, you're not supposed to use this point here, right? That's why there's a hole in the graph. We have to use this point, and that goes along with this, right? So if x equals 0, the output is supposed to be 1. And so that's our answer. So I want to look at one more graph to kind of contrast with that one. And this one's not actually going to be a piecewise function, but I'm choosing it to kind of demonstrate a point about limits. So let's say instead that we're just trying to find the limit as x approaches 0 of just sine of x. So not a piecewise function, just the regular graph of sine of x. So what would this look like? Well, it would look just like the one above, except for that it would not have a hole at x is equal to 0, right? It would just be like normal graph of sine of x. So in this case, if we look at the limit as x approaches, and let me just grab a different color for that. If we look at the limit as x approaches 0 from the left of sine of x, well, we're just looking at, where's the graph heading? And the graph is heading towards 0, so the answer would be 0. And if we look at the limit as x approaches 0 from the right of sine of x, well, the graph is going down, 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 getting closer to 0, so the answer would also be 0. And so therefore, because the left and the right hand limits agree, the overall limit is equal to 0. And then in this case, if you actually plug in 0, well, now there's nothing funny going on, right? Because it's not a piecewise function and because it's defined at 0, you can just plug in 0. And sine of 0 is 0. So this is kind of a funny example, and in some ways it's easier, but it might seem a little strange compared to the last one. And the reason it might seem strange is that this is not really a situation in which you have to use limits, right? So the whole kind of purpose of limits is that they allow you to describe what's going on in a function when you can't plug in a number. So this one, because there's nothing wrong with 0, you can just plug in 0, there's not really much of a point of taking a limit, but you can. And if you take it, you just get 0 as your answer. And the other thing I just wanted to point out is that notice that these graphs are exactly the same except for what's happening at 0. And so remember that when I was talking about limits, I kept saying, or I keep saying, that it doesn't matter what's happening at that x value. It only matters what's happening around it. And so because these two functions are exactly the same except at x is equal to 0, that's the reason that their limits are all the same. Because the limits don't care what's happening at 0. They just care about like what's happening around it. And so because everything else is identical except for what's happening at 0, that's why you get the same answers on this graph and this graph. So that's an idea that we'll actually get into a little bit more in the next video when we'll be talking about using algebra methods. That actually really ties back to this idea of if you have two graphs that are identical except for at one point, then they have the same limit. Okay, so the last example I want to do is going to be another piecewise function, but this is one where we're not going to have a formula for it. So we're just going to do some limits basically just by looking at this graph. And I would encourage you at this point to pause the video and try some of these yourself, because I think now that we've done all these other examples, hopefully you'll be kind of warmed up and be able to do them. So this function is f of x, so let f of x be the function graphed below. So we're going to focus on like 3 different parts of the graph, basically. So the first thing I want to do is find the left and right hand limits as x approaches -1. So the limit as x approaches -1 from the left, the limit as x approaches -1 from the right. So I know it's a little confusing with this negative n plus, but just remember that the little exponent, that just is talking about from the left and the right. This negative sign is just -1, the same way that you would always talk about negative or positive number. And then we'll find the limit as x approaches -1 of f of x. And then the last thing we'll do is f of -1. And then we're going to do the same thing at x is equal to, let's see, -3 and x is equal to 1. So I'll write those down as well, and you can get started if you want on figuring out all of those. So we'll do the limit as x approaches -3 from the left, the limit as x approaches -3 from the right, the limit as x approaches -3 overall, and then I'll just squeeze it in here. We'll also do f of -3. And then last one will be 1. So the limit as x approaches 1 from the left, the limit as x approaches 1 from the right, and the limit as x approaches 1 overall, and then we'll also do f of 1. Okay, so hopefully you got to try these yourself, and then now we'll go over the answers. So focusing first on negative, I guess actually let's go left to right. So let's start with -3. So if we're evaluating the limit as x approaches -3 from the left, we're seeing like where's the graph heading if we're coming in from the left approaching -3. And the graph is heading towards a height of 2. And so that tells us that the left-hand limit is 2. And then from the right, we're plugging in values that are getting closer and closer to -3 from the right. And so that looks like the graph is heading towards a height of 3. And so because the left and the right hand limits do not agree with each other, we would say that the overall limit does not exist, or you can write DNE as like a shorthand for that. And then f of -3, that's where we just look at the graph and we say, well, if I'm actually going to an x value of -3 and trying to plug it in, where is the point on the graph that actually has an x value of -3, and it's this point here. So f of -3 is equal to 3 because the point -3, 3 actually lies on the graph. So one thing that we'll see as we go through this is that sometimes f of, when you actually plug in the number, sometimes it agrees with one of your limits, the left and the right. Sometimes it doesn't agree with either of them. So it really depends on the situation. You want to just kind of take it case by case. Okay, so next up we have -1. So if we're approaching -1 from the left, our y values are getting closer and closer to 1, right? The graph is trending towards a height of 1. And so the limit from the left is 1. If we're now taking the limit as we approach from the right, well, now the graph again is actually still just getting closer and closer to a height of 1. And so the limit is still 1. And so because those two agree with each other, because both the left and the right were equal to 1, that tells us that the overall limit is also 1. And then evaluating f of -1, well, now again, we're just looking at where, if we were to try to plug in -1, where is there a point on this graph that has an x value of -1? And it's not here, right? Because that has a hole. That hole is specifically meant to denote that there is no point there. And so we have to go up here and we see, oh, okay, that's the point on the graph that has an x value of -1. And so f of -1 is equal to 4. So this is an example where the left and the right limits agree, but the actual point on the graph does not agree with the limit. Whereas on the last one, the left and the right did not agree, but when you plugged in the number, it actually agreed with one of the two sides. So it just really depends on how the piecewise function is set up. Okay, so the last one we're going to do is we're going to be approaching 1 from the left and from the right. So if we approach 1 from the left, the graph is getting closer and closer to a height of 5. So the limit as we approach 1 from the left is equal to 5. If we approach 1 now from the right, sorry, I'm just going to scooch this over a teeny bit. So if we approach 1 from the right, now we're looking at, as we get closer and closer to 1 coming in this way, what is the, where are the y values going? And in this case, they're actually going up and up and up and up, right? This is a vertical asymptote on the right-hand side. So that would tell us that the limit is infinity. And so because the left and the right-hand limits did not agree, we would say the limit does not exist. And then what about f of 1? Well, if we look at the graph, we try to look for a point at an x value of 1, right? And so if you go up here, you see, okay, well, there's something, but that doesn't count because it has a hole. And then this vertical asymptote, so the whole kind of reasoning behind vertical asymptotes is that they never actually touch that particular x value. So that tells us that there is no point on this graph at an x value of 1. And so f of 1 in this case does not exist. All right, so that is it for today. And the worksheet that goes with this video will give you a bunch more practice with both sketching piecewise functions, with evaluating limits of piecewise functions, and also an example kind of like this one where you're just given a graph and you have to find limits from that graph. All right, I'll see you all in the next video.